Hi guys, welcome back to another video. Today we're going to be looking at 2021 IMO Problem 5, a nice combinatorics problem from the 2021 IMO. And here's a question. Two squirrels, Bushy and Jumpy, have collected 2021 walnuts for the winter. Jumpy numbers the walnuts from 1 through 2021 and digs 2021 little holes in a circular pattern in the ground around their favorite tree. The next morning, Jumpy notes that Bushy has placed one walnut into each hole, but has paid no attention to the numbering. Unhappy, Jumpy decides to reorder the walnuts by performing a sequence of 2021 moves. In the kth move, Jumpy swaps the positions of the two walnuts adjacent to walnut k. And we want to prove that there exists a value of k such that on the kth move, Jumpy swaps some walnuts a and b such that a is less than k is less than b. Now this problem statement is a lot to digest, so let's break it down. So first we have 2021 little holes in a circular pattern around the favorite tree. So we can just model it as such. So we have hole 1, hole 2, hole 3, all the way to hole 21. I'll draw it a bit better. So these are the holes, the spaces. And originally Bushy puts one walnut in each hole. So all of them are labeled. So we end up going 1, we could have 2019 here, we could have 773 here, 2 here, and so on and so forth. And we could have like 71 here. And on every single move, Jumpy decides to reorder the walnuts by performing 2021 moves. On the first move, when k equals 1, we swap the positions of the two walnuts adjacent to walnut k. So we end up going from 71 and 2019 all the way to 2019 and 71, and this is 2 here. Then for the n equals 2 case, the k equals 2 case, we swap the 773 with whatever numbers over here. So we go from 773 to whatever numbers here. Let's suppose that number is like 59. Then this process continues, where we just do this for every single walnut. And we want to prove that there exists a value of k such that we swap walnuts a and b such that a is less than k is less than b. Now notice that we're doing things about walnut k. So if we have something like 25971, then if we end up swapping walnut 59 in this exact configuration, then we are done because 2 is less than 59 is less than 71. So we kind of have this increasing pattern going for us. All right, so now how do we solve the problem? Well, one thing that I want to note first is that these type of problems, it may seem like they get solved a lot by invariance. And this is generally the case for a lot of these problems. However, I now want to present the invariant or give the motivation for the invariant, but instead I want to discuss this problem as a whole and just explore the problem. And the solution will come naturally after some exploration. Anyways, now we have the number 2021, so that's a bit too large for our purposes. We can't do anything efficient when we start with 2021. So let's start with a smaller number, 3 walnuts. Then we have 3 walnuts around the tree. Then we have 1, 2, and 3. Then when we swap 2 and 3 around 1, because whenever we move at 1, we have to swap 2 and 3 because those are the other 2 walnuts. So when we do that, we get 2 and 3. And then when we use walnut 2, then we swap 1 and 3. But 1 is less than 2 is less than 3, and that solves the n equals 3 case. So not that bad. But now we have to look at the n equals 4 case. So let's suppose that we have our 4 walnuts here, And since we can just rotate things, we can just assume that this is 1. Now, where can the 2 go? Well, if it goes here, then that means that whatever this number is, it could be 3 and 4. On the first move, we swap 2 and 3. So that goes from there to here. And then on move 2, we swap 1 and 4, and 1 is less than 2 is less than 4. Something similar happens in the other case. So that means that we do not want 2 to be on the edge, because the only other case is when we have 2's over here. Then we can put 3 here and 4 here. Let's see if this situation works. On move 1, we swap 3 and 4. So that becomes 4 and 3. On move 2, we swap 4 and 3 again. And 4 and 3 are both greater than 2, so that again doesn't work. There should be 2. Then this again becomes 3, 4. On move 3, we swap the 1 and 2. 3 is greater than both 1 and 2, so that doesn't work. But when we do that, we get 2, 1. Finally, move 4, we swap 2 and 1, and 4 is greater than 2 and 1, so that doesn't work. So we have to go 1, 2. And we just went through all our moves, so that means that when we have 4 walnuts, that means that it doesn't work. And this is because we have all of the large numbers surrounding the small numbers, and all of the small numbers surrounding the large ones. For example, the 3 and 4, which are larger numbers, surround the 1, while the smaller numbers 1 and 2 surround the 3. In general, we can find a similar construction that shows that an even number of walnuts does not work, because we can place 1, 2, 3, 4, and then 5, 6, 7, 8. Where the 5, 6, 7, 8 here, like these are the large values. And the 1, 2, 3, 4, these are the small values. So the reason why even and do not work is because we can distinguish between these large and small values in a very organized way. And we're hoping that for odd values of n, we can't really do this in an organized way. And looking at the even n case, this motivates us to try considering large walnuts and small walnuts. So let's see how this works out. Suppose we have n equals 5 walnuts, because 5 is the next odd number that we haven't discussed. So we have 1, 2, 3, 4, 5, and walnut 1 is over here. And suppose we just randomly label the walnuts like 5, 3, 2, 4. Or let me go ahead and make it a bit. There we go. Then when we use move 1, we swap the 5 and 3, and both of those are large walnuts. We want to somehow categorize large and small. So let's assume for now that 1 and 2 are small, and 3, 4, and 5 are large. And our hopes are that if we swap a small walnut and a large walnut, then that will satisfy the problem statement. So when we apply move 1, we end up swapping 2 large walnuts. So that gives us 2, 5, and 3. So that's 3 and 5. On move 2, we end up swapping 2 large walnuts again. So that gives us 4 and 3. Now on move 3, that's when we swap a small walnut and a large walnut. And that means that we're done. So we need to somehow refine this argument, because recall what we did for the n equals 2 case, the k equals 2 case, where after we swap these guys here, so that's 3 and 5, then if the 1 is right next to the 2, then we need to somehow incorporate this. We need one to be small and some other ones to be large. Because if it's 1, 2, 3, that requires 3 to be large, which is not necessarily the case when we look at n equals 7, for instance. The point is that we need to somehow change our definition of small and large. So this motivates the following. What happens if we change the definitions of small and large such that at any point when we swap a small and large, then we're done? Well, let's see how we can do this. Suppose that we apply a move on walnut number 4 in this configuration. Then we want 2 to be small and 5 to be large. And this would mean that 1 is small as well, because 1 is less than 2. Then that means that we don't know what happens with 3 or what happens with 4, but we can just assume that everything beyond 4 is large, because if the 3 was next to the 2 instead, then it would be 3, 4, 5, so that would mean that 3 is also small. And when we have 4 and 5, because we're looking at walnut 4, we can just arbitrarily assign like 4 to be small. So on the fourth move, the walnuts 1, 2, 3, and 4 are all small, and 5 is large. And that's basically the only way we can get it such that when we swap a small walnut and a large walnut, then we are done. Can we extend this idea? Well, of course we can. Suppose we have our 5 walnuts again. So we have 1, then 5, 2, 3, 4. This is a slightly different configuration. Then on the first move, we classify this one as small and all the other ones as big. Then big, then big, then big. And then on the first move, we end up swapping 4 and 5. So that becomes 4 and 5. And on the second move, now we want 2 to be small as well. So this is also small. Then we end up swapping 3 and 4, which are both big. So again, doesn't really give us anything. So 3 and 4. Now, on the third move, we end up marking 3 as small. So this is small. And now we're swapping 2 small numbers. So this goes from 1. So this goes 1 and 2. Then on move 4, we turn walnut 4 into a small one. And then on move 4, we swap 2 and 5. And we're just done. Because we swap a small walnut and a big walnut. Alright, so now that we reduce it to this, where one walnut becomes small every single time, it just suffices to show that we swap a small walnut and a big walnut at some time. And because if we have 2 small walnuts and we swap them, then that does not change whether they are small or not, because 4 is still small and so is 1 when we swap them. So swapping 2 walnuts does not change anything unless we get a winning move. So in fact, we only really care about the labels that numbers have. So we start with all the numbers as being big, 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 and big. Then on the first move, we make the first walnut small. So that means that this one becomes small. And then we end up swapping these two. Does not change the fact that they're big. On the second move, we can make another walnut small, which is walnut number 2. So suppose we make this one small. Then we end up swapping the 2 big ones again. And that doesn't change anything. On the third move, we can choose walnut 3 and make it small. So we can choose this one here, and that becomes small. So this is small, and now we swap to small walnuts, so that becomes small, 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 big, big. And that doesn't change the configuration. On move 4, we choose any of these guys to become small, so we can choose small here. And then we have small and big, and those swap, and we're done. All right, so now we reduce it to showing this. If we make one walnut small every single time, then at some point, we're going to get the sequence BSS or SSB. Because notice that we always swap at a small walnut by definition. And when we have SSB, we end up swapping the small walnut and the big walnut, and we're done. So we want to show that we have SSB somewhere. Now, suppose that we make our first move and make this S. Then we want SSB, which means we want some consecutive S's. So this means that we want to try looking at the number of consecutive S's. In this case, there are 0 consecutive S's. In this case here, when we replace this B with an S, there's still 0 consecutive S's. When we do this one here, then there are 2 consecutive S's. And that doesn't really help much, because suppose we only increase the number of consecutive S's by 1, then that means that we have to add the S on the edge somewhere. Meaning that if we add the S here, then this one cannot be an S. And we end up swapping those two and we're done. So we want the number of consecutive S's to increase by 1 and exactly 1 at some point. Now suppose that it never increased by 1, then that means that it increases by either 0 or it increases by 2. Because it can increase by 2 if we change this B to an S here. It can't increase by 3 or more for clear reasons. So suppose that we increase it by 0 or 2 every single time. That means that the number of consecutive S's at the end will be an even number. But let's count the number of consecutive S's. There are just 5 pairs of consecutive S's, which is an odd number. So we can't get to 5 with only 0 and 2, which means we have to have a 1 somewhere, and this finishes the case. And obviously this doesn't just work for n equals 5, it works for any odd number, including 2021. So basically this just solves the problem. So what are our main takeaways from this problem? Well, the first is to not immediately look for invariance. And this is a key lesson. Sometimes with combo problems, the key is not to just look for invariance or certain tools that just kill the problem, but instead the main goal for combo problems is to just play around with them and enjoy them for a bit. And after playing around, the main idea should come naturally. For example, the main invariant came from the even n case and why that didn't work, and trying to modify big walnuts versus small walnuts. In fact, a bunch of the solutions to this problem completely ignore the words small and big, and instead of saying small and big, it is painted pink or unpainted. And that just completely ruins the motivation, because we're naming them small and big because that stays true to our motivation. Because we want to swap a small walnut and a big walnut. That's the intuition here. And we can't just fix the definition of small and big, because if we could swap 2 small walnuts, then that could be it, and we don't know it. So we have to change the definition of small and big somewhere. And that just gives a solution. And on that note, the second lesson is to just enjoy. It should be enjoy the problem. As we didn't with this case. We just went in with an open mind, not looking for anything, and just experimenting with things, just like how I explained in lesson 1. And the solution came naturally. Alright, so that's all I have to say for now. Thank you so much for watching this video. Please subscribe if you'd like to see more.